Hi everyone, today I'll be talking about support vector machines. You can find all my sampled Python code on GitHub at a dash of data. First, I'll go through some SVM basics, starting with a visual introduction, and then a step-by-step walk through some sample code in Python. And then I'll talk about how you can fine-tune your model with some additional complexities, and then I'll give you my final thoughts on SVMs. So let's start with what is a support vector machine? Well, it's a classification technique. So what does that mean? So let's say we had all these blue dots and all these teal dots, and I asked you to classify this data. So another way to say that is if I had asked you to split the data. Well, what would you do? You could split the data this way, or this way, or this way. All of those ways work. But what if I asked you to split the data in the best possible way? Well, then you would probably say that this line best splits that data. So at the end of the day, that's essentially what a support vector machine is. It's this model that best splits this blue and teal sections. So why is this the best split? Well, let's say that that line in the middle there, that's the median of a road, and that these are the two lanes of the road. So in this case, this is the widest road that separates these two groups. So if we go back and look at some of those other lines that we had used to split the data, you can see that they create some pretty narrow roads. But this one here, this is the widest road that separates the two groups. So let's add in some more technical terms now. So instead of saying this is the widest road that separates the two groups, we can say that this is the widest margin that separates the two groups. Another way to say this is the distance between the points and this line are as far as possible. So again, these points here, these can also be called support vectors, and this line here, this can be called the hyperplane. Okay, so those are all our technical terms. So let's summarize all this again. If I had asked you to split this data in the best way possible, you can now say that this is the hyperplane that best splits the data because it's as far as possible from these support vectors here, which is another way of saying we have maximized the margin. Okay, so how do you maximize the margin? Well, this is actually a constrained optimization problem. So there's two parts there, the constraint and the optimization piece. So let's break it down. The reason that you're trying to optimize something is because in this case, we're trying to maximize the margin. And the reason that there are constraints is because our constraint here is that these dots here, they can't be on the road. They have to be away from the road. So we have our constraints and we have our optimization. So this is a constrained optimization problem. So the way to solve a constrained optimization problem is to use Lagrange multipliers, which involves quite a bit more math, so I'm not going to go through it here in detail. But now we've covered the basics visually of how SVM works. So now what? Well, let's apply this to a real-world problem. So my other passion in life, second to data science, is baking. So these are all things that I've baked in the past. And the one I wanted to focus on here are these cupcakes. So every time that I make cupcakes, my husband and I always have this debate on cupcakes versus muffins. He thinks that they're exactly the same thing, except that a cupcake just has frosting and a muffin has random bits of stuff in it. So being the experienced baker that I am, I completely disagree, and I just know that cupcakes and muffins are inherently different, like their batter is different. And so I decided to challenge myself and create a classifier to classify recipes as cupcakes or muffins. So that way, once I've built my model, when I give my model a new recipe, it should automatically predict whether that recipe is a cupcake recipe or a muffin recipe. So there are 3 steps I need to take to do this. First, I need to find the data. Then I'll apply a data science model, which in this case will be SVMs. And then finally, I'll review the results. So first, let's find that data. Well, the way I did this was I went to Google and I Googled basic muffin recipe and basic cupcake recipe, and I recorded the top 10 muffin and top 10 cupcake recipes. So surprisingly, muffins and cupcakes just have 8 ingredients in them. And then also surprisingly was all 20 recipes were different. There were no duplicates in there. But then as I started looking into this data, I noticed that there were some problems. So my main problem was that each recipe yielded a different amount of batter. So one cupcake recipe might have had 1 cup of flour. Another cupcake recipe would have 4 cups of flour. And because those values were so different, if I were to put that data straight into my model, it would actually see those 2 recipes as being completely different, even though they were both cupcakes. So I realized the first thing I had to do was normalize my data. And the way I did this was I took my data from being amount-based. So for instance here we have muffin 1 having 2 cups of flour, half cup of sugar, and so on, to percent base. So muffin 1 is 47% flour, 24% sugar, and so on. And so at the end of the day, this is what my data look like. So you can see for every row, I've labeled it as a muffin or a cupcake, and then I have all my ingredients here, and each row adds up to 100%. All right, I found my data. So the next step is to apply a data science model. So to do this, I wrote a Python script in Jupyter Notebook. So I followed 6 steps here, and I'll go through each of them in detail. The first is to import libraries. So I imported a few libraries for analysis. So you can see pandas, numpy, and sklearn. And then I imported another couple libraries for visuals. So we have matplotlib here, and then seaborn to make things beautiful. The next thing I did was I imported my data. So from my pandas library, I used the read.csv function, and you can see that the data looks pretty good here. And then before I fit my model, what I always like to do is visualize the data to see if it makes sense. So I decided that out of the 8 ingredients, I wanted to plot 2 of those ingredients. So in this case, I chose sugar and butter because I baked for a long time and I just had a feeling that those 2 ingredients would be most likely to differentiate muffins and cupcakes. And so when I created the scatter plot here, you can see I was right. Those muffins are on the bottom left there, and they have very little sugar and very little butter, whereas cupcakes have a ton of sugar and a ton of butter. And so when you look at this, you can see it's actually a pretty good candidate for SVM. So the next thing I'm going to do is fit the model. So we had talked about sugar and butter before, so I'm going to use those 2 ingredients as inputs for my model. And then I'm also going to input all the labels, so that one column that you saw before that had all the muffins and the cupcake labels. And then I'm going to put them into a model here. So you can see that I'm using svm.svc. So what SVC stands for is support vector classifier. So there's also SVR, which is for regression, but that's not used as commonly. But you need to specify SVC for classification, which is what support vectors are typically used for. And then also here you see that I've set the kernel equal to linear. So I'm going to talk about kernel a little bit more later on in the presentation, but just wanted to let you know that for the basic case, you want to set kernel equal to linear. And then you can fit your model, and on the bottom there you can see our output. So that output doesn't mean much, so let's visualize it. Okay, so the visualization steps are actually quite lengthy, so I'm going to go through them quickly, but you can review the code in detail on GitHub. So here I've created a hyperplane along with the dotted lines for the margins, and I'm plotting all of that onto a plot that you see here. So on the left you can see that this is our SVM model, and on the right you can see that we've maximized the margin. All right, so now I've applied a data science model. So the next step is to review the results and see if they make sense. So just to reiterate, the challenge was to classify recipes as cupcakes or muffins. And when given a new recipe, determine if it's a cupcake or muffin recipe. So let's go back to our code. So what I've done here is I've plotted one additional point, that yellow point right there, and that's a new recipe. And so visually, you can tell that that recipe is supposed to be a muffin because it's with all the red dots. But we want our model to predict that automatically. So let's see if our model can do that. So here I've created a function called muffin or cupcake. And what you need to do is input the amount of butter and sugar that that recipe has, and then it'll tell you the answer. So down here, I put in my new recipe that has 12 parts butter and 12 parts sugar, and it tells us that we are looking at a muffin, which is correct based on the visual on the last slide. So at the end of the day, we see that muffins and cupcakes are not the same thing, but they're actually different, and you can classify them using support vector machines. So I won that argument. All right, so that was our basic case, but let's talk about how to make SVM even more powerful. So there are 4 things that I wanted to go through in this additional complexities section, starting with higher dimensions. So for the last bit of slides, we've been working with 2 dimensions, sugar and butter, and we were able to separate that using a line. So let's say we wanted to add another dimension. So let's say flour. Then we would have 3 dimensions, and we could separate that data with a plane. Let's say we had 4 dimensions. Well, in that case, we'd separate our data with a hyperplane, but it gets pretty hard to visualize. But here's the cool thing. Even though it's hard to visualize, it's actually very easy to code. So here is our original code, and we were putting in the butter and sugar ingredients. You can see that data right there. So let's say we didn't want to just look at 2 dimensions, but we wanted to look at all 8 ingredients. Well, all we have to do is input all 8 ingredients here, and the code will automatically take this information and run the model. And so the reason that we want to add in more dimensions is because with more dimensions, there's the opportunity to further maximize that margin and create a better model. Okay, moving on to C parameter. So on the left here, you can see this is the data that we've been working with, and we were able to separate it with a line pretty easily. But I actually hid one piece of data from you. So this is what the original data actually looked like. And you can tell there's this red dot on the top of the screen there. And if we were to create that line on the left, you see that that red dot actually gets misclassified. So this is where the C parameter comes in. So the C parameter allows you to decide how much you want to penalize these misclassified points. So if you look at our original code again, you can see the C parameter was hiding in our output here. So the default value for the C parameter is 1, but you can vary it. So here are some visuals to help you better understand this. So on the left here, I've given the SVM model a low C value, 2 to the negative 5th, and on the right, a high C value, 2 to the 5th. And so you can see the difference in the 2 models here. On the left, the model just allows that point to be misclassified, and on the right, there's no misclassification. So on the left here, with a low C parameter, we are prioritizing simplicity. So this line here is also called a line with a soft margin because we're allowing that misclassification. On the right here, we're prioritizing making as few mistakes as possible. So there's few mistakes here, but in this case, we're probably overfitting because this model is just so close to all those blue points. If you were to bring in a new recipe in the future, it might actually classify that incorrectly. So how do you pick the best C parameter? Well, what you need to do is try different values of C all the way from, let's say, 2 to the negative 5th to 2 to the positive 5th, and then see what the best C value is for your model. All right, let's also talk about multiple classes. So one cool thing about SVMs is it doesn't just classify 2 classes, it's also able to classify more than 2 classes. So in this case, I've added some green dots here, and these are your scones. So this is what a scone looks like for those that don't know. And with SVMs, you can actually classify your data into 3 different groups here. So on the left we have our muffins, in red we have our cupcakes, and on the right we have our green scones. So how can you do that in the code? Very easily. So all you need to do is add this parameter called decision function shape, and you can set it equal to OVR or OVO. So what do those mean? So OVR means one versus rest. So what it does is if you had, let's say here, you had 3 different groups that you wanted to classify, what OVR would do is it would try its best to classify the blue group versus all the rest of the data, create that hyperplane, and then it would try to separate the red group from the rest of the data, and then the remaining data it would put into the green group. On the other hand, we have OVO, so it would compare all the classes separately and create a hyperplane for each one of them, and then combine all that information. So there's some pros and cons to both here. So the pro to the OVR approach is that there are fewer classifications that need to be made. So let's say we were actually classifying 10 different groups. Well, in that case, we would have to create 9 different models. So it would create a model for one versus rest for every single class, and then for that 10th class, that's just where the remaining data goes. And then for the OVO technique, if you were to classify every class against the other with 10 different classes there, it's actually a combination of 10 take 2, which is 45 different classifications, which takes a very long time. But the pro to the OVO technique is that it's less sensitive to imbalance. So let's look at the left side there, the OVR side. So if you were to classify the blue group versus, let's say, 9 other groups, that blue group is really small. The 9 other groups might just overpower that blue group and just say that nothing is part of that blue class. So that's a bit of imbalance right there, whereas on the OVO side, that wouldn't happen as much because you're just comparing one class at a time. So it's really up to you what technique you want to use. All right, finally, I want to talk about the kernel trick. So no SVM presentation is complete without the kernel trick. So let's say that we had this data on the left here. We have some red dots and some blue dots, and I asked you to draw a hyperplane to separate that data. Could you do it? You'll probably try to draw a line like this, and that doesn't work. But we're still able to separate this data with SVM by using the kernel trick. So what the kernel trick does is think of it as adding another dimension to this data. So what this kernel trick does, in this case, you see it's taken that data on the left and added a dimension, a z dimension, so that you can now linearly separate that data with a hyperplane. Okay, so there are a couple different kernel options in Python. There's the linear kernel, radial basis function, RBF, polynomial, and sigmoid. So I just want to say here, you can see that even though you weren't able to separate with a line in 2 dimensions, by using that kernel trick, if you project that graph on the right into 2D, you can see that it becomes that graph on the left. Okay, so what does this look like in the code? Well, our original code, our kernel was set to be linear, but in our updated code here, you can see I've set kernel equal to RBF. So that's a really popular one to try out. And with RBF, you need to set 2 additional parameters, so a C parameter and a gamma parameter. So we talked a little bit about C already, but now I want to talk more about gamma. So on the left here, you have just our basic linear kernel, and I've set C equal to 1. And then for the right 2 graphs, those are 2 more graphs with RBF as the kernel, and C is still equal to 1, but I varied the gamma here. So I varied it from 2 to the -5th all the way to 2 to the 1st. And immediately you can see the difference between the two gamma values. So with a small gamma value, there's less complexity. So it's kind of like that small c value here. You're seeing it's allowing those misclassifications. And then on the right, you see with this large gamma where we're overfitting big time. So it's pretty much classifying everything as a cupcake, which at the end of the day, if you're eating muffins, scones, or cupcakes, you are essentially just eating a cupcake. But you can see here that it's actually not a good model, so you'd probably want this lower gamma in this case. But how do you choose the best gamma? Well, you're going to have to try a bunch of different C and gamma combinations using grid search and see which one is best for your data. All right, so that's all I had for SVMs. I wanted to also just mention when you should use SVMs. So about the pros, there are a couple pros of SVM. One is that it's good at dealing with high dimensional data. So you saw with the kernel trick that it's able to use high dimensions effectively. Also, it works well on small data sets. So in our case here, we just had 20 different recipes that we were looking at. So it's a pretty small data set, and SVM was able to classify that data pretty well. The main con is that picking the right kernel and then also the right parameters can be very difficult and computationally intensive. So if you were having to run this SVM model on 10 different C parameters and gamma parameters, that would just take a really long time, and it's probably not the most effective way to build a classification model. So in that case, there are some other classification techniques you can use that I've listed here, and there's no set way of figuring out which one is best. My advice to you would be just to try multiple techniques on your data set and see which one works the best on your data. All right, that's all I have on support vector machines. Again, you can find sample Python code on GitHub at a dash of data. Thanks.